the current path is leading us to a disaster. Companies like OpenAI and other leading labs, they haven't come up with any convincing solutions to the hard parts of the problem, and they don't even have the tools to do that because of lack of theoretical understanding. What the companies are doing is basically just developing things in trial and error. That's kind of a band-aid method, which is to say it works until it doesn't work.
Discussing the future of AI tends to get philosophical. What does it mean to have goals or understanding? Is power seeking a default consequence of wanting things, or a human quirk resulting from our unique evolutionary history? What motivates kindness? Framing questions in this way makes them accessible, allowing everyone to participate in the conversation. But this lack of precision also makes such questions intractable, as disagreements become a clash of intuitions. Today's guest on Guardians of Alignment is Vanessa Kosoy, who works for the Machine Intelligence Research Institute, or MIRI, on building mathematical theories for safe AI. This focus on understanding from first principles puts her work in stark contrast to the move fast and break things experimental approach of leading AI labs. In this interview and elsewhere, Vanessa defends the value of a more theory-based approach and explains what it means to explore machine learning as a basic science.
I've always been an autodidact, so I kind of just tend to learn things by myself. When I was little, I thought I will be a theoretical physicist. I actually have a bachelor's in math, but after completing a bachelor's, instead of going to academia, I decided to go for a career in the industry instead, in software. So I had a long career in the software industry, specifically in algorithm engineering, mostly computer vision, various roles, algorithm engineer, team leader, R&D manager. I also had my own startup. I was a consultant. And then something like 10 years ago, I got exposed to this whole topic of existential risks from AI and started thinking that, well, that's actually seems kind of important. So I started pivoting to that. And initially, it was just me doing research in my free time. Then it was supported by MIRI. And then I also got, more recently, also got support from the Long-Term Future Fund, which enabled me to go full time.
So, what was that process like? You were working just self-directed way, I presume, and then later you gained support from MIRI and other sources. How did that come about?
I just started reading some of the stuff MIRI were writing and people on LessWrong were writing, and I had my own ideas about that. I started working on my own ideas and writing posts and LessWrong mostly about that. After that, I got invited to some workshops, some events. And eventually, MIRI said that just, well, it seems like you're doing some nice work here, so maybe we will also pay you for it. And I was great because that also enabled me to do more of that and spend less time doing other things. So, yeah.
So a little background for the audience here. Less Wrong is a blog, a very popular blog. It's initially on rationality, but also on AI related things. And then MIRI is the Machine Intelligence Research Institute. I like to describe them as the people working on alignment before it was cool. Tell me a little bit more about MIRI as an institution.
MIRI were more or less the first to talk about existential risks from artificial intelligence. Eliezer Yudkowsky started talking about this in the year 2000, and initially MIRI was just like Yudkowsky, and then like over the years you managed to get some funding and then get other researchers on board, and they were thinking about this question of how do we make artificial intelligence safe, and how do we even approach the question, what kind of mathematical theory we can come up with to solve this question. That's even before the deep learning revolution started, and way before the whole hype with large language models in the recent years. So they have most of their time have been committed to trying to come up with some foundational mathematical theory that will help us with AI alignment. More recently, they pivoted more to outreach and trying to influence policy because of their beliefs that the timelines are really short and we don't really have time for developing this theory. unfortunately.
Have you been a
That's
part of that pivot in terms of now doing more outreach, or are you still continuing to do the theoretical research as before, and it's just MIRI's doing less of that?
Yeah, no, my outlook is different. I'm more conservative, you could say. I think that the timelines are not quite as short as a lot of the people in the ARS community believe. And I think that if the effort in the policy channels to regulate AI development and to delay AI development, to stop the really dangerous kind of AI from coming about will succeed, then it's only buying us time. And then like the question is buying us time for what? And I think that theoretical foundations is definitely still the most important thing among the things that we should be doing with the time that we have, or with the time that we will succeed to buy by some policy plan one way or another. I think that practically in any world, creating this foundational theory is the key. And that's what I'm doing. That's definitely where my personal skills and advantages lie, in working on math and not on policy.
You mentioned timelines intuitively, and it's impossible to really predict these things with any kind of precision, but just in terms of like what motivates you, what do you kind of see as your timeline for when this stuff needs to be solved?
Well, I mean, some people think that, AGI is coming in 10 years or even less. I think that's a little extreme, but when things need to be solved, the sooner the better, right? Like, if we have the solution in 5 years, then we're in a better place than if we only have the solution in 10 years, which is still better than if we only have the solution in 20 years and so on. Realistically, my personal opinion is still that chances are that there are still multiple decades before we actually arrive at the sort of AI that poses existential risks. So that kind of gives us a little more time, but not infinite time.
Describe that realization. What made it click for you that this is something that you want to work on?
It actually started as more like a curiosity, because it actually started with me discovering completely randomly, you could say, some papers on AGI, not even on AI alignment or risk or anything like that, but just some paper by Jürgen Schmidhuber and Marcus Hutter with some ideas about AGI. And I always was a math nerd, so it seemed really cool that there are those mathematical frameworks for thinking about AGI. I started reading about that, and eventually also found Less Wrong, where some people were also discussing this kind of thing. Then well, on the one hand, I was reading more and more things that Eliezer Yudkowsky wrote on the topic and people on Less Wrong wrote on the topic, but I also started thinking about the mathematical models. Eventually, it clicked to me that when you're thinking about the actual math, then it makes perfect sense that there's no mathematical reason why AI would have to, care about humans or care about anything at all aligned with what we as humans care about. And on the other hand, it also seemed obvious that it could be much more capable than us. It's pretty clear intuitively, I think, but for me, I like to understand everything through math. So for me, when I saw that you could actually put that into a mathematical model, then it really clicked for me that this is the real thing. This is something we should really be concerned about.
This idea that there's no reason to assume that AI will necessarily be nice, that sounds a lot like the orthogonality thesis that Bostrom wrote about, that you can have intelligence on one hand and how nice it is on another thing, and they don't have to go together, or any set of values can go with any level of intelligence. Is that essentially what the insight was?
Yeah, that's exactly the orthogonality thesis. I mean, it's not. In hindsight, it seems just like an obvious thing, but for me, it was necessary to see that you could actually think of it in terms of mathematical objects, like values could be formalized as a utility function, and then an agent could be formalized as some kind of a optimizer, some kind of a bias optimal policy or whatever for this utility function, you could actually put rigorous meaning behind each of those terms and see that it actually all makes sense. It's not just some kind of a philosophical hand-waving trick.
What, in your view, is the fundamental reason that makes the problem of AI alignment hard?
I think the problem is hard. I think that what makes it hard is, well, first of all, that we're aiming at a very narrow target because human values are very complicated and specific. We care about a lot of very detailed things, love, friendship, beauty in our own subjective understanding of it, sex. All of those things are kind of human things that exist because of some complicated accidents of evolution, the way it happened on some very particular planet, some very particular point in history of a particular universe. This set of values is a very, very narrow fraction of the huge space of possible values, or huge space of possible minds that you could imagine. So most minds are definitely not anything that would be nice to us by our standards. Worse than that, there's also this phenomenon which Nate Soares formulated nicely in one of his relatively recent posts, where he wrote that there is a basin of attraction around agent capabilities, but there is no basin of attraction about agent alignment. So what it means is that if you apply enough optimization pressure, even with brute force techniques, you will eventually generate highly capable agents. And an example of that is evolution, right? Evolution is a very, in some ways, very primitive brute force algorithm that eventually created the human brain, which is a much more sophisticated algorithm. If you put enough brute force optimization into looking for things that are successful in open world environments, eventually you will come across intelligent agents. And this is even before you put in recursive self-improvement in the equation, which makes it even stronger as this kind of basing of attraction where you converge to, whereas nothing of the sort is true about being aligned to human values in particular. It's very plausible that we could, by just kind of blind or semi-blind trial and error, arrive at creating highly capable agents much before we understand enough to actually make those agents aligned.
That sounds like going against the other Bostrom popularized idea of instrumental convergence, that things like survival will be wanted by almost any system, optimizing hard enough.
There's this notion of instrumental convergent goals, which are certain goals that most intelligent agents will pursue because they help them to achieve their terminal goals, whatever their terminal goals are. And these are things like survival, like gaining more resources, becoming more intelligent, and so on and so forth. But human values are not that. If we manage to construct an AI that survives and gains a lot of resources, that's nice for the AI, I guess, but that doesn't help us in terms of alignment to our values at all. That's a very different kind of thing.
Does the issue of modern AI being trained on human-generated data and existing in human society not help?
I think it helped, but it kind of leaves a lot of questions. One of the questions is, okay, you learn from human-generated data, but how do you generalize from there? Because it's really not clear what conditions are needed to get good generalization, especially when the concept you're learning is something extremely complicated. The higher the complexity of the concept you're learning, the more data points you need to learn it. What we're doing with the so-called large language models, which are the hype in recent years, is trying to imitate humans, which is, nice. It could even lead to something good with some probability, not very high probability. But the problem with it is that in order to use that, you need to generalize far outside the training distribution. Here, we actually need to look at what the goal is. The problem is that it is technically possible to create super intelligent AI, which will be dangerous. To solve this problem, it's not enough to create some kind of AI which would not be dangerous, because otherwise I could, write an algorithm that doesn't do anything. That's not dangerous, mission accomplished. We need to be able to create AIs that are sufficiently powerful to serve as defense systems against those potential dangerous AIs. Those have to be systems that have superhuman capabilities at building sophisticated models of the world and building complex long-term plans based on that. And that's something that is far outside the training distribution of a large language model or like anything that's based on human imitation. It is extremely unclear whether we can actually rely on the algorithms we have to generalize that far out of the training distribution without completely losing all of their alignment properties.
LLMs are fundamentally imitative, which doesn't seem particularly dangerous in itself, but it also limits what it can do. And so we can't really expect that that's just going to stop here. Eventually, there might be something like reinforcement learning added onto it. Maybe not necessarily that algorithm, but something that can be as creative as Alpha Zero is in Go and finding a really creative move that no one's seen before. So we need to be prepared for things that are very much more powerful because those are going to be useful. And the economics that led to building LLMs are going to lead to building bigger things. Is that roughly what you're getting at with that preparedness sense?
Yeah, that sounds pretty much on the spot. Either it will be reinforcement learning or, well, I don't want to speculate too much what is needed in order to make AI more powerful because that's not good information to have out there.
Fair enough. Moving on a little bit more to the things that you actually work on. One idea I've seen as adjacent to this is the term agent foundations and also the learning-theoretic agenda. What are those things?
Agent foundations is kind of this abstract idea that says we need to create a foundational mathematical theory which explains what agents are. Like what does it mean mathematically for an algorithm to be an agent? What types of agents are possible? What capabilities they can or cannot have, and so on. The learning theoretic agenda is more specific than that in the sense that it's like a very specific program that is trying to achieve this goal, specifically by tools that build on statistical and computational learning theory, algorithmic information theory, control theory, this kind of thing. So this is basically kind of the program I created to answer this challenge of coming up with those agent foundations.
Okay, so agent foundations is like the question of how do minds work that encompasses AI, and learning theoretic agenda is like how do we design algorithms that like push this in a good direction. Is that right?
I wouldn't put it that way. I would just say that like agent foundations is just trying to understand how minds work, and people have been trying to do it in various ways. Like MIRI have historically had all sorts of proof theoretic models that try to approach this, and then there's Gerber's logical induction, and there's various ideas under this very broad umbrella. Whereas the learning theoretic agenda is a very specific approach. It's kind of this approach that starts with AIXI and kind of classical reinforcement learning theory as the starting points, and then kind of looks what are the missing ingredients from that in order to have a foundational theory of agents and start building towards those ingredients, towards those missing ingredients with ideas such as Infra-Bayesianism and Infra-Bayesian physicalism and metacognitive agents and so on.
The kind of agents and minds that you're talking about here, is this tied to the frontier large language models, or is it more broad to AI or any kind of thinking entity?
When I say agent, I mean something very broad, much broader than existing AIs or even just AIs, certainly like including humans or potential aliens or whatever. So for me, an agent is a system that has particular goals, and it is learning sophisticated models of the world in which it is embedded, and uses those models to build long-term plans in order to achieve its goals. So this is kind of the informal description of what I mean by an agent. And then like the whole goal of this program is to go from this to a completely formal mathematical definition and study all the implications of this definition.
So not even beyond LLMs, it's even broader than machine learning. What's the reason for that approach, given how dominant machine learning is? Why not focus on the things that seem to be the most widely used?
Yeah, so first of all, let's do some order in the terminology. I would distinguish between AI, machine learning, and deep learning. AI is kind of this thing that people started thinking about since the 1950s, about how to build thinking systems without really having good understanding of what does it even mean, but just some kind of intuitive notion that there is such a thing as thinking and we should be able to replicate it in a machine. Machine learning is a more specific approach to this that kind of emerged. Well, I don't want to point the finger exactly when, but probably something like the 80s. Machine learning talks about specifically this idea that the central element of thinking is learning. And learning means that you're interacting with some unknown environment and you need to create a model of this environment. So you need to like take the data that you see and use it to create a model. And that's analogous to how scientists do experiments, gather data, and then like build theories based on this data. And this kind of general idea is called machine learning, or more accurate would be to call it just learning. The machine part comes from trying to come up with ways to actually implement this inside a machine. This is a field that has a lot of mathematical theory. The mathematical theory behind machine learning is what's known as statistical and computational learning theory, and that's actually the foundation of the learning-theoretic agenda. That's why it's called learning-theoretic. There has been a hypothesis that this kind of notion of learning captures most of the important bits of what we mean by thinking. And I think that this hypothesis have been extremely well supported by recent developments in technology. And this is something that I completely endorse. And this is basically the basis of my whole research program. So there's no contradiction here because learning is still a very general thing. Humans also do learning. Aliens would also have to do learning. Deep learning is a more specific set of algorithms to how to actually accomplish learning efficiently in a machine. And that's what started the deep learning revolution around 2010, although the algorithms existed in some form for decades before that. But it took a while to get the details right and also to have the right hardware to run them. So deep learning, its unfortunate feature is that we don't understand it mathematically. So a lot of people are trying to understand it, but we don't have a good theory of why it actually works. That's why it's not the focus of my research program, because I'm trying to come up with some mathematical understanding. I definitely have a hope that eventually people will crack this kind of mystery of how deep learning works, and then it will be possible to integrate the theory I'm building with that other theory. Even if we had this theory, then it still seems really important to think in the broadest possible generality. Because, well, first of all, we don't know that the algorithms that exist today will be the algorithms that bring about AGI, but also because the broadest generality is just the correct level of abstraction to think about the problem, to get at those concepts of what does it mean even for a system to be aligned, because there are some philosophical problems that need to be solved here, and they are in no way specific to some very particular algorithm. And also there is the fact that I actually want this theory to also include humans in some ways, because I might want to use this theory to formalize things like value learning, right? How do I design an AI system that learns values from humans?
Seeing the Wikipedia level or just browsing the internet description of machine learning and deep learning, it's very easy to use them interchangeably. Like I think I've seen the description as deep learning is just the idea that you add multiple layers of neurons. And so because there's multiple layers, it's deep.
Yeah, so let me try to clarify the distinction. Machine learning talks about taking data and building models from it. The type of model you're building can be very different. Before deep learning, we had algorithms such as support vector machines. Polynomial regression is also a very simple type of machine learning. Fitting a model to data. Various methods using statistics can be regarded as sort of machine learning. So there is some space of models or space of hypothesis, and you're trying to use the data in the optimal way to infer what the correct hypothesis is, or to have some probability distribution of her hypothesis if you're like doing a Bayesian approach or whatever. But different types of hypothesis classes lead to very different results in terms of the power of the algorithms, but also in terms of what do we know to say about how to learn those hypothesis classes, and what do we know to prove mathematically under which conditions we can actually learn them. For example, for support vector machines, the mathematical theory is basically solved. Like for kernel, there's like kernel methods that build on top of that, and that also has very solid mathematical theory. Deep learning is a particular type of learning algorithm which uses those artificial neural network architectures. It's not just multiple layers. There's a lot of details that matter. For example, the fact that the activation functions are ReLU, that turns out to be pretty important. Or what kind of regularization method you use in training, like dropouts is basically what kind of started the deep learning revolutions, essentially. If you're working with sequences, then we have transformers, which is a very specific network architecture. So there is actually a lot of very specific details that people came up with over the years, mostly with the process of trial and error to just see what works. We don't have a good theory for why those specific things work well. We don't even understand the space of models those things are actually learning, because you can prove theoretically that if you take a neural network and you just let it learn another neural network, then in some situations it will be infeasible. But for real world problems, neural networks succeed to learn a lot of the time. And this is ostensibly because the real world has some particular properties that make it learnable, or there's some particular underlying hypothesis class that the neural networks are learning and which captures a lot of real world phenomena. But we don't even have a mathematical description of what this underlying hypothesis class is. We have some results for some very simple cases like 2-layer or 3-layer neural network or some other simplifying assumptions, but we're not close yet to having the full answer.
Deep learning assumes certain things about how the world is in terms of what it can pick up, and it happens to work fairly well, but it's not really clear what it's assuming.
Yeah, that's exactly right. So we have different no-go theorems which say that for arbitrary data, even if the data is fully realizable, so even if the data is such that the neural network can perfectly express an exactly correct model, even if these cases, in general, the problem is infeasible. In general, gradient descent will not converge to the right model, and also no other algorithm will converge because the problem will just be intractable. There are some properties that the world has, and since this deep learning is successful in such a big variety of very different cases, it feels like those properties should have some simple mathematical description. It's not like some properties that are extremely specific to text or to audio or to images. It's some properties that are extremely general and hold across a wide range of different modalities and problems. Those are properties that I can just speculate that could be, for example, properties that have to do with compositionality, which have to do with how the real world is often well described as being made of parts and how things can be decoupled according to different spatial scales or different temporal scales on which the dynamics is happening. But we don't have a theory that actually explains it.
To get a little more concrete about this, you mentioned ReLU as one of the examples of a thing that just works. As I understand it, ReLU is basically like taking the output and it'd be kind of being like a graph where it's flat on one side and a diagonal line past zero. So just get some input and run it through this function to change the output in this way. Whereas before it would use a sigmoid, which was kind of more like a smooth line. And for some reason, ReLU works better. And the sense I'm getting from your explanation, or at least in the direction of why, is that this impacts what kinds of things the neural network is able to understand. And so it expanded it or changed it in a direction that's more matching with reality. But it's all these things are come up with a throw stuff at the wall and see what sticks kind of way and just measure the results without really understanding why ReLU is better than sigmoid.
I mean, that's more or less right. We have to just be careful that when we say what the neural network can understand, it's a pretty complicated concept because it's not just what the neural network can express with some set of weights, but it's what the neural network can actually learn for a process of gradient descent. So it has to do not just with the space of functions that the neural network can describe, but with the entire loss landscape that is kind of created in this kind of space of weights when we look at a particular data set.
When you're describing a gradient descent and loss landscape, the analogy I hear thrown around a lot is like a ball rolling down a hill. There's a constant gravity force, and you want it to get down to sea level, but often it doesn't because it finds some local minima or just like a hole or something where any direction it goes is up, and so it's not going to roll anymore. It's not just what the neural network can learn and express, but also how these design choices shape the landscape so that down always gets you to sea level.
Yeah, that's a pretty good explanation. Gradient descent is something that we have good mathematical theory for how gradient descent converges to the global minimum for convex functions, but the loss for neural networks is non-convex, but it still happens to be such that it works. People have gained some insights about why it works, but we still don't have the full answer for it.
Okay, so if the landscape is really bumpy, then you kind of don't expect it to get to the base, but it does somehow. And that kind of framing raises a lot of just immediate questions of unpredictability. Like if you don't know what this landscape looks like, then where's that thing going to end up? You mentioned AIXI at one point. What is that?
AIXI is this idea by Marcus Hutter, which is supposed to be a mathematical model of the perfect agent. The way it works is there is a prior, which is the Solomon prior, which, for those who don't know what that is, it's basically some way to mathematically formalize the concept of Occam's razor. Occam's razor is this idea that simple hypotheses should be considered a priori more likely than more complicated hypotheses. And this is really at the basis of all rational reasoning. What Hunter did is he took Solomonov's prior, which is a very clever way to mathematically formalize this notion of Occam's razor and say, well, let's consider an agent that's living in a universe sampled from the Solomonov prior, and this agent has some particular reward function that it's maximizing, and let's assume it's just acting in a Bayes optimal way. So it's just following the policy that will lead it to maximize its expected utility according to this prior. And let's call this AIXI, which is a really cool idea. Only it has a bunch of problems with it, starting from the minor, in quotes, problem that it's uncomputable. There's not an algorithm that exists to implement it even in theory.
I think I heard it, AIXI explained once as imagining the entire universe described as a bunch of bit ones and zeros. And at the start, all of them could either be a 1 or a 0. Then you get a little bit of data, and now you've locked in a few of those numbers. And now with each one, you've cut the space of all things it could be in half. As you keep learning, you get more and more certain.
It's actually a little more nuanced than that because, well, just the fact you have a lot of possibilities doesn't mean that it's uncomputable, because maybe the exact thing is uncomputable, but you could still imagine that there is some clever algorithm that approximate this Bayesian inference process. So for example, if you look at classical reinforcement learning theory, then there are things like algorithms for learning an arbitrary Markov decision process with n states. So Markov decision process with n states, it still has an exponentially large space of possible ways it could be, and would still have actually efficient algorithms that converge to the right thing out of this exponentially large thing by exploiting some properties of the problem. The thing with AIXI is that its prior is such that even individual hypotheses in the prior are already arbitrarily computationally expensive, because in its prior, it considers every possible program. So every possible program that you can write on a universal Turing machine is a possible hypothesis for how the world works. And some of those programs are extremely expensive computationally. Some of those programs don't even halt. They just enter infinite loops. And you can't even know which, because this is the halting problem, right? This is why the AIXI is a setting where it's kind of a non-starter for doing something computable, not to mention computationally tractable.
The minor problem of uncomputability aside, a perfect algorithm. What does that mean? Does that make it safe if it were somehow magically computed?
No, it doesn't make it safe in any way. It's perfect in the sense of it's the most powerful algorithm you could imagine. Again, under some assumptions. I mean, there are other problems with this. It assumes that the outside world is simpler than the agent itself. So there are like multiple problems with this, but if you kind of put all those problems aside, then you could argue that this is the best possible agent. And in this sense, it's perfect. It's very, very, very not safe. Like, in order for it to be safe, we would need to somehow plug the right utility function into it. And that would still be a very non-trivial problem to understand how to do that.
What kind of algorithms do you look for?
I'm imagining that there will be something that I call the frugal universal prior, which is some kind of prior that we can mathematically define, which will simultaneously be rich enough to capture a very big variety of phenomena. And on the other hand, we'll have some clever algorithm that can actually allow efficient learning for this prior, using, for example, some compositionality properties of the hypothesis on this prior, or something of that sort. But even knowing this prior, there's a lot of other conceptual problems that you also need to deal with, like what I call the problem of privilege, where the formalization of Occam's razor kind of privileges the observer, and you need to understand how to deal with that. Then there's the problem of realizability, where you cannot actually have a hypothesis which gives you a precise description of the universe, but only some kind of approximate or partial description, and you need to understand how to deal with that fact. Then there's also the fact that you want your utility function to be not just a function of your observations, but also some parameters that you cannot directly observe, and you want to be able to deal with that somehow. You also want to be able to prove some frequencies guarantees for this algorithm, so to know how much data this algorithm actually needs to know to learn particular facts and have like a good theory of that. So there's like a whole range of different questions that come up when studying this AIXI-like models.
Studying AIXI-like models, that is what you're working on?
You could, yeah, if you wanted to put it in one sentence, I guess.
What are some interesting problems that you're interested in solving? I've seen Newcomb's problem floating around and stuff adjacent to this.
Newcomb's problem is a problem that Eliezer Yudkowsky wrote about a lot as something that's very confusing for classical accounts of rationality. You have two boxes that you need to choose from. One box has $1,000, the other box has either nothing or $1 million, and you can either choose the first box, or you could take the money that's in both boxes. And normally, taking the money that's in both boxes is always strictly superior to just taking the one box, except that in this thought experiment, there is some entity called omega, which can predict what you do, and so it only puts the $1 million in the other box if it knows that you will only take that box and won't try to take the $1,000 box as well. So only if you're the type of agent that would predictably for omega take only one box, only in this case you will get out of the room with $1 million. Whereas in the other case, you will only have $1,000. So arguably it's better to take one box instead of two boxes, as opposed to what many classical accounts of rationality would say. This is one example of an interesting thought experiment. For me, this thought experiment falls under as a special case of the problem of non-realizability, where like you need to deal with environments that are so complex that you're not able to come up with a full description of the environment that you can actually simulate. Because in this example, the environment contains this agent omega, which simulates you, and this means that you cannot simulate it, because otherwise it would create this kind of circular paradox. I've actually also showed that my theory of dealing with non-realizability, which I call Infra-Bayesianism, actually leads to optimal behavior in this kind of Newcomb-like problem scenarios.
And the Newcomb problem, like the reason for looking into that is not because we expect to be faced with a omega offering us boxes at some point, but because it's just a visible way of thinking about like, how do I deal with things when I can't know what's going on? And also like, yeah, it might be easy to say, yeah, well, I'll just take one box because I'll get more that way. But then when you really dive into what's a coherent, non-hand wavy reason as to why, then there's some interesting insights that can potentially come up from that. Have there been any discoveries that you found through exploring these kinds of things?
I would say that Infra-Bayesianism itself is an interesting discovery, that some theoretical account of agents that can reason about complicated worlds that are much too complicated for the agent to simulate. Now I explain it usually, I kind of motivate it by stating the problem of non-realizability. But the way I actually arrived at thinking about this is through thinking about so-called logical uncertainty. The reason people started thinking about it was because of so-called updateless decision theory, which came from thinking about Newcomb time paradoxes. So it all comes from that line of reasoning, even though after the fact, you can motivate it by some much more general abstract motivation.
What's the connection between these decision theory type questions and making a safer AI?
The idea is creating a general mathematical theory of agents. The way it's going to help us with making AI safer, there are several reasons. The most obvious reasons is that having this theory, we hopefully will be able to come up with rigorous models of what does it mean for a system to be an aligned agent? And having this rigorous definition, we'll be able to come up with some algorithm for which we can prove those algorithms are actually safe agents, or at least we could have some conjecture that says that this given modulo such and such conjectures, we think that those algorithms are safe agents. Like in cryptography, we have some conjectures which have very strong evidential support. We could have at least some semi-formal arguments, because now when people are debating whether a particular design is safe or not safe, it's all kind of boils down to those hand-waving philosophical arguments which don't have any really solid ground. Whereas this gives us tools for much more precise, crisp thinking about this kind of question. It hypothetically also gives us much more power to leverage empirical research, because maybe we will be able to take the empirical research we have, plug it into the mathematical theory, and get some answers about how we expect those results to actually extrapolate to various regimes where we haven't tested it.
Would this line of research that you're working on eventually be usable in evaluating things like large language models or deep learning based systems to be able to say with greater certainty the extent to which they're safe or unsafe?
I think that there are multiple paths to impact. So there is a path to impact where we will eventually come up with a theory of deep learning, if not like a fully foolproof theory, then at least some strong conjectures about how deep learning works that can interface with the theory of agents I'm building. And then we could use this composite theory to prove things, or at least to have like strong arguments about properties of systems built on deep learning. There could be a different path to impact where we use this theory to come up with a completely new type of algorithm for building AI, which are not deep learning, but for which we have a good theoretical understanding. There's also some third possibility that we won't have a good theory, but we could at least reason by analogy, similarly to how many deep learning algorithms are designed by analogy to some algorithms for which we have mathematical theory. Like deep Q learning is analogous to simple Q learning, for which we have a mathematical theory. So we could also imagine a world in which we have some kind of idealist toy model algorithms for which we have some rigorous arguments why they are aligned, and then we have some more heuristic algorithms which we cannot directly prove things about, but which are arguably analogous to those toy models.
So I heard three paths to impact there. One was potentially building a different form of AI from the ground up that's verifiable right from the beginning and does the same things as deep learning based AI, but in a more rigorous sort of way. A second one is evaluating or better understanding deep learning or whatever is state of the art. And then a third in between the two is having a simpler form of AI that analogizes to the state of the art things that you can use to understand the other one better.
Yeah, that sounds about right.
I'd like to focus a bit on using foundational research to understand other things like deep learning, getting at this theory-based approach, bringing in like a total opposite counterpoint. One could argue, no, you should just look at the things that are being used and collect data about it, and then build your theory by finding patterns in the data. When the theories are wrong as a result of more data, then update it then. Why work on theory in advance?
The biggest reason is that you cannot really reliably extrapolate from empirical research without having an underlying theory, right? Because you might, for example, take some measurements and find some trend, but then there is some phase transition later on that you don't see in the trend, but which happens and behavior changes to a completely different regime. And because you don't have a theoretical explanation, you won't notice, or people will just switch to using completely different algorithms which behave in completely different ways. So you might have those empirical models that you have of existing AIs, but those empirical models are very myopic. They're always looking one step ahead, and then you don't see the cliff 3 steps ahead of you. Updating those theoretical empirical models on new things that happen, it might just be not quick enough. Like eventually you fall off the cliff, and then it's too late to say, oh, actually that trend line was wrong, but it's already too late. luckily, we are in a domain where we have tools to do research even without empirical data. Or, of course, we should use the empirical data we have, but we're not necessarily bottleneck on empirical data because the thing we're studying is algorithms. And algorithms are mathematical objects, so they can be studied mathematically. And this is very different from just studying some phenomenon, like, just some phenomenon of physics, where if you don't have the data, then there's no way to generate the data without having it. Whereas here, this really should all boil down to math. Well, or more precisely, it should boil down to math plus whatever properties the real world phenomena have that we want to assume in our mathematical theory. Here it is like something that we need empirical input for. But on the other hand, we already have a really good understanding of physics. So given the knowledge of physics and other scientific domains that we have, it's very plausible that we just have enough information to answer all the questions purely through mathematical inquiry, even if we had no empirical data at all, which is not to say we shouldn't also do empirical data to kind of supercharge this research, but we're not limited to that.
So it's not a choice between theory versus experiment. We should be using both. You're focused on the theory side, and arguably there's not enough work on that, and that's where the bottleneck is, not on just getting more data.
Yeah. I think we should definitely be doing both. Ideally, there needs to be synergy where experiments produce new phenomena for theorists to explain, and theory inspires the experiments. The theorists should be telling the experimentalists which questions, what kind of experiments are the most interesting, and we should have this kind of synergy. But I think that in the current landscape, definitely in AI alignment, the theory side is the side is currently left behind, and that's where I think we should put the marginal efforts in.
Do you see that synergy existing now? Like, is OpenAI asking MIRI for feedback on their experiments? Or is there any kind of connection, or are they just people siloed off from each other?
I think it doesn't exist now almost at all. I mean, okay, no, to be fair, it exists in some areas and exists much less in other areas. For example, there's people working on singular learning theory. There's this new oracle, Timaeus. I think that they are much more interfaced with experimental work, which is good. The kind of research that MIRI is doing and the kind of research that I'm doing is much less interfaced with experimental work. I have some plans for creating an experimental group working in closed loop with me on those questions as part of my big long-term plans, but I still haven't gotten around to doing that.
If you could change anyone's mind or set political agendas or business kind of things, what would you like to see happen to have more of an interface?
Well, I think first of all, we just need more theorists, because to have an interface, we need something to interface with. So we just need more theorists for one thing. I think that's in practice, that's where the bottleneck is now. Once this progress in theory gets sufficiently paced, there will be a bunch of questions. I mean, there are already questions that I would like to see experiments on, but the more this thing picks up, the more such questions we have. I think now the main bottleneck is just in having more people working on the theory.
What would change from an external perspective if there was a lot more theory work? I imagine a skeptic could argue here that, like, hey, the OpenAI and these other companies are making these really awesome breakthroughs in a largely experimental kind of pace. It's working great. If it ain't broke, don't fix it. What's broken in your view?
I think that the current path is leading us to a disaster. I think that companies like OpenAI and other leading labs are wildly overconfident about their abilities to solve problems as they come along. I think that they haven't come up with any convincing solutions to the hard parts of the problem, and they don't even have the tools to do that because of lack of theoretical understanding. We don't even have models that are precise enough to have a solution in which we could really be confident. We need to be very precise about the arguments we make, which convince us that the solution is good. And we don't even have the tools to reach this type of precision. What the companies are doing is basically just developing things in trial and error, If we see any problems, then we'll just tweak the thing until the problem goes away. And that's kind of a band-aid method, which is to say it works until it doesn't work. It fixes problems on a superficial level, but eventually there will come a point where either the problem will not be caught in time and the results will be catastrophic, or the problems will be caught in time, but then nobody will have any idea what to do in order to fix it. And eventually someone is going to do the catastrophic thing anyway. The only thing which makes me perhaps less pessimistic than other people in MIRI, for example, is because I think we still have more time. I don't think they're quite as close to AGI, and I think that a lot of things can change during this time, which is, again, not to say they will change. We might burn all this time and still end up with a catastrophe.
What's an example of an existing problem that only has superficial solutions?
The real problem we're concerned about is not really an existing problem, right? The main thing we're concerned about is that future AI systems, which will be much more powerful than existing AI systems, will bring about extinction of the human race or a catastrophe on a similar level. That's not an existing problem for the simple reason that the AI systems we have today are not capable of learning a model of the world that's so sophisticated that it enables you to do this type of actions. But we see that even the problems that we have, the companies kind of struggle with. All the things that happen with large language models, where the infamous jailbreaks, where they're trying to make them well behaved in various ways, not telling the users offensive like dangerous information, for example, and the users easily find jailbreaks to work around that or tell false answers. But again, for me, that's not the real problem. That's just an analogy. I mean, they're kind of struggling with this very simple, much easier problems now, which is not to say they won't solve them. Trial and error will get you eventually. The reason trial and error is not the solution for existential risk is because once everyone are dead, the trial is over. There's no more trial. The problems we have now, they're still struggling with them because they don't have like principal tools to solve them. But eventually they will trial and error their way through and will patch them somehow, or at least they'll solve them well enough for it to be economic. But once you reach the point where failures are global catastrophes, trial and error is no longer an acceptable method of fixing the problem.
Obviously, we don't get to see lots of test data of the world ending. But I would imagine there'd be some precursor issues that are smaller but hint at what's to come. Do you see the challenges with hallucination or not being able to control what the AI says as those kind of precursors, or totally irrelevant, or there's something else? Or is this the kind of thing you're looking at, there just won't be any precursor issues?
It's kind of a difficult question because there are really very important bits that are still missing from existing AI systems to produce the kind of risks. So we can point at examples where systems are kind of misgeneralizing. There's a lot of famous examples, some program that wins Tetris in quotes by pausing the game forever, or that wins some boat race game by racing the boats in infinite circles, doing various weird unintended behaviors because the metric that the algorithm is maximizing is not actually what the users intended. So you could call those precursors, but I feel like it's not exactly capturing the magnitude of the problem because those are still toy settings. They're not kind of open world systems that are acting in the open physical world. The goals that they're trying to solve are much simpler than human values. There's not really operating domains where there are really complex ethical considerations. Maybe large language models are starting to approach this because they enter domains where there are like some, at least morally, not completely trivial issues that come up. But on the other hand, large language models are not really doing things that are strongly superhuman. Well, they might be superhuman in the sense that they have like a very large breadth of knowledge compared to humans, but not in our senses. So it's kind of hard. I mean, there are things that are sort of analogous, but it's not really strongly analogous. But then again, our motivation to be concerned about this risk doesn't come from looking at LLMs. Like Eliezer Yudkowsky starting talking about those things before deep learning was a thing at all.
Yeah, I guess the reason I was asking about it is in the places where the stuff gets debated and polarized, one of the common objections is that, oh, there's no evidence behind this. This is all just storytelling. Is there evidence of the danger, or does it really come from looking at the math?
The problem is, what do you call evidence? Because that's really a very complicated question. The things that would be like obvious evidence would be things like AIs completely going out of control, breaking out of the box, hacking the computer, copying themselves to other computers, outright manipulating human operators, and so on. But this kind of thing, this is a sort of canary that you only expect to see very, very, very close to the point where it's already too late. It's not possible to say that we will only rely on this type of evidence to resolve the debate. Other type of evidence, some people can say that evolution is sort of evidence how a machine learning algorithm can produce something which is completely unaligned with the original algorithm. Other people show you reinforcement learning algorithms doing not what the designer intended. But for every argument like that, you could have a counter argument which says, yeah, but this example is not really similar. We cannot really project from there to existential risks because there are some disanalogies. And yeah, there will always be some disanalogies because until you have AIs in the real world that are very close to being an existential risk, you won't have anything that's precisely analogous to something presenting an existential risk. So we have no choice but to reason from first principles or from math or by some more complicated, more multidimensional analysis. We just have no choice. The universe doesn't owe it to us to have a very easy empirical way of testing whether those concerns are real or not. One of the things I'm hoping for is that the theory will also bring about strong arguments for the dangers. Or if the theory will tell us that no, everything is fine, then we can also all relax. But the lack of theory is part of the reason why we don't have foolproof, completely solid arguments in one direction or the other direction.
The challenge with finding evidence is that anything you can point to that exists now could be interpreted in multiple ways. Having solid theory would lend some credence to one interpretation over another.
Yeah, absolutely. Like if you have a theory that says that a particular type of misgeneralization is universal across most possible machine learning systems, and we also see this type of misgeneralization happening in real machine learning systems, then it would be much harder to dismiss it and say, oh yeah, here we have this problem, but we'll do this and that will solve it easily.
One thing that's still bugging me about the issue of evidence not being available now is the analogy my mind immediately goes to is climate change. You could say that, like, oh, the idea of large swaths of the world being uninhabitable and, all sorts of other things is just this elaborate story, that's never happened before. Why would you believe that? Humans have never made the earth uninhabitable. But then you can look at a bunch of things that exist already of like small scale disasters, the graphs of CO2 versus temperature and all that sort of thing, and point to say like, hey, the really bad stuff hasn't happened yet, but there is a lot of evidence. What makes AI different from that?
Yeah, I think that climate change is a great analogy because the big difference between climate change and AI is that in climate change, we have really good theory. Like in climate change, we have physics, right? And we have like planetary science, which is on a very, very solid foundations. And we have computer simulations. It's still not trivial. There are some chaotic phenomena which are hard to simulate or predict. So not everything is completely trivial. But still, we have some very, very strong theoretical foundation for understanding how those things work and what are the mechanisms. And this theory is telling us that there's still big uncertainty intervals around how much exactly degrees of warming we're going to get with such and such amount of CO2, but we still have a fairly solid prediction there. Whereas with AI, we don't have this. Like the analogous situation, if you want to imagine like a climate change AI style, then it would be something like not having a theory which explains why CO2 leads to warming, having some empirical correlation between temperature and CO2, and then people could argue ad infinitum correlation is not causation. Maybe the warming is caused by something completely different. Maybe if we do some unrelated thing, it will stop the warming, which is not actually true. We would be in the dark. And with the AI, we're currently in the dark.
What is happening currently with your work at MIRI?
There are multiple problems I'm looking at. Hopefully, we'll publish very soon a paper on imprecise linear bandits, which is related to Infra-Bayesianism that I mentioned before, which is like a theory of agents that reason about complicated worlds. So that's analyzing this theory in some very simple special case in which I succeeded to get some precise bounds for how much data an algorithm would need to learn particular things. After that, I'm starting to look into the theory of learning state representations in reinforcement learning, which is currently another big piece missing from the theory, which is kind of how your algorithms should learn about which features of the world are actually important to focus about. There's also, in parallel, I have a collaborator, Georgi Such, who works on using my theory of Infra-Bayesian physicalism to create a new interpretation of quantum mechanics. He has some really interesting results there. It's kind of a test case which demonstrates how this framework of thinking about agents allows you to solve all sorts of philosophical confusions. In this case, it's like confusions that have to do with the interpretation of quantum mechanics. Other people like in MIRI are working on other stuff. Scott Gerben has some project about some new type of imprecise probability, some new way of representing beliefs that has some nice compositionality properties. Kaspar Osterheld from Carnegie Mellon and Abram Damsky had a paper recently about some new type of frequencies guarantees for algorithms that are making decisions based on something that's similar to a prediction market. So yeah, a lot of interesting things are happening.
Are there any other questions that have been on your mind that I did not ask that you feel would be really helpful in someone seeing this getting a sense of what you're about here?
Not a question exactly, but I also have a more concrete approach to how to actually solve alignment, how to actually design an aligned agent, which I call Physicalist Superimitation. Is a kind of variation on the theme of value learning, but it draws from the framework of Infra-Bayesian physicalism, which comes from the Learning-Theoretic agenda and from some ideas in algorithmic information theory to come up with some interesting, well, at this point, kind of semi-formal approach to how you could have an AI that learns human values in a robust way. It deals with a lot of problems that other approaches to value learning have, like how do you determine where are the boundaries of the agent? How do you take into account things which are the internal, the agent, which is the human in this case? What is a human? How do you locate this human in space? How do you take into account things which are not just behavior, but also internal thought processes of the human in inferring the human's values? How do you prevent perverse incentives such as the AI somehow changing or manipulating the humans to change the human values? Or how do you avoid the inner alignment problem? It answers a range of concerns that other approaches have.
This sounds reminiscent of inverse reinforcement learning.
Inverse reinforcement learning is this idea that we should look at behaviors of humans, infer what those humans are trying to do, and then we can do this thing, we as an AI. So I actually have presentations in which I explain Physicalist Superimitation as inverse reinforcement learning on steroids. Right. It's taking this basic idea, but implementing it in ways that solve a lot of the deep problems that more simplistic approaches have. One problem that simplistic approaches have is that they model humans as perfect agents that follow a perfect policy given perfect knowledge of the environment, which is wildly unrealistic. Instead, I model humans as learning agents that kind of just learn things as they go along. And they also might even do that imperfectly. Another thing is the issue of boundaries. What is a human exactly? Where do you put the boundaries around a human? Is there just some particular input and output port which the human uses, and you consider everything that goes through this port to be the human? But then how do you deal with various discrepancies between what goes into this port and what the human actually intended to do, or various possibilities like the AI actually hijacking this channel and so on? In my approach, instead, the way human is formalized is that a human is a particular computation that the universe is running, and this is something I can actually formalize using Infra-Bayesian physicalism. It has particular properties which make it agentic. So the agent detects which computations the universe is running. Among them depends which computations are agents, And amongst those agents, it selects which agent is its user by looking at the causal relationships, and this way it homes onto the boundary of the agent. The first thing is because we're talking about the computation that this human is running, which is human reasoning regarded as a computation, we're also automatically looking at internals and like internal thought processes and not just things that are expressed as external behaviors. So we have like potentially much more information there.
What would be the best way for someone to get involved, and what would they want to learn in advance?
One thing they could immediately start doing is just reading up on stuff people did in agent foundations and in the Learning-Theoretic agenda until now. I have this recent post, Learning-Theoretic Agenda Status 2023, which summarizes a lot of the things. Also have a reading list post where I recommend some background reading for people who want to get into the field. More concretely, in terms of careers tab, so it's already too late for apply, but now I'm running a track in MOTS, which is a training program for researchers who want to get into AI safety. So I have a track focused on the Learning-Theoretic agenda. Hopefully there will be another such track next year. Actually, I have a fantasy of having an internship program which would bring people to Israel to work with me on this. Currently, because of the war, this thing has been postponed, but hopefully, eventually things will settle down and I will revive this project. These are currently the main ways to get involved.
Thank you very much for that description. Wish you the best in developing this theory and gaining more interest so that mismatch between evidence and theory starts to get corrected and the researchers know what they're doing rather than stumbling in the dark.
Thank you for having me.